So we're going to take a look at our organic analysis, looking at our two test tube reactions, thinking about distinguishing between aldehydes and ketones, but also how we can use our oxidation of alcohols to distinguish between those. Other organic analysis techniques is our infrared spectroscopy and our mass spectrometry, which we'll have a look at in a moment. But to start with, if we think about our aldehydes and ketones, there are two different test tube reactions that you could use for this. So the first one is Tollens reagent, and this starts off as colourless, and this will change to a silver mirror if an aldehyde is present. If it's a ketone, it will remain colourless. For our feelings, we start off again with a solution, but this time it's a blue solution, and this forms a brick red precipitate if an aldehyde is present. Whereas it will remain blue if a ketone is present. So the idea here is our ketone can't be oxidised, and so the solutions remain the same. Whereas our aldehyde can be oxidised to a carboxylic acid. And so here we get a colour change. With our oxidation of alcohols, our primary alcohol, secondary alcohol, these can both be oxidised, whereas our tertiary can't be oxidised. And so you'd have no change. Visible. This is because in order to oxidise this, you'd have to be breaking the C-C bonds. Remember that our groups are alkyl groups. Whereas with our secondary and our primary groups, we've got CH bonds that we can break, and that's much easier to do than the C-C bonds. So for our primary and secondary alcohols, we oxidise these using acidified potassium dichromate. And here we get a colour change from orange to green for our primary and our secondary, however no visible change for that tertiary. Our primary goes to form an aldehyde, which we know can also be further oxidised to a carboxylic acid, whereas our secondary goes on to form a ketone, and that can't be further oxidised. Infrared spectroscopy, here we can use the table of data of our absorptions to identify bonds which are characteristic of functional groups. E.g., you could distinguish between a C-C bond and a C-O double bond. You could also use the fingerprint region, which is unique to a compound, and you could compare this to known compound spectra and see if they overlap perfectly, then you know that it's a match for that one. with our mass spectrometry, we get our relative molecular mass from that. Particularly our high resolution mass spectrometry can be useful for this in identifying between different isotopes which would have the same molecular formula mass if you rounded, but not using this high resolution. You also end up getting MR+1 peaks, which gives you information about the isotopes present, and your MR+2 as well. So thinking about your carbon isotopes, your chlorine and bromine isotopes. Then also with our mass spectrometry, we can look at our fragmentation patterns to try and get an indication of how the bonding is in that compound, as to where the bonds have been broken in order to make these fragments.